Okay, so welcome everybody again. So now we continue with Marco Eamon from the Federal University of Minas Gerais. We're talking about convolution of periodic multiplicative functions and the divisor problem.
Okay.
Marco?
Thank you very much. I would like to say that it's a great pleasure for me to be back here in IMPA. I was a PhD student here, master and PhD student, and I always was in this side. It's a great pleasure to be here in this side, in this wonderful auditorium, Ricardo Mayen. And it's I would like to say a few words in name of the organizers and myself. We are very happy to organize for the first time this conference here. And we are very happy that all of you came here. And just an advice for the foreigners that are coming to Brazil for the first time, be wise with caipirinha and picanha. Okay. So this work actually is the second paper of a series of 2 papers. And the main result that I'm going to present here was done, let me mark my time here. So the main result here was a collaboration that I have done last year in my sabbatical time in Marseille under the supervision of Olivier Ramaré here. And so the main result was done in collaboration with these people, Gopal Maiti, that at that time he was a postdoc in Marseille Université, with Olivier Ramaré, that I already introduced, and with Priyanvad Srivastav, that if I'm not mistaken, he was finishing a postdoc in Göttingen, right? Yeah. Well, so you are seeing that picture there from a dessert. Is not totally random picture because we was in Marseille, and you must know that in Marseille it stays the CIRM, the Center for Conferences. And one thing that made me very happy at that time is that we have in Marseille University you have the seminar from the group GDAC, that is Geometry, Dynamic, and Arithmetic. And after the talks, most part of the times, you have a lunch at the CIRM restaurant, which is very good food. And that is a dessert. And the speaker have a free lunch, actually, if I remember correctly. And so in my visit to Marseille, I gave 3 lectures and a mini course of 4 lectures. And I angry with Olivier because he really have to tell me that the T-shirts in Marseille are the large size is small size, actually, compared to the Brazilian. So at the end, I went to try to buy a T-shirt from the CIRM, and my size was okay. So let's stop with joke in this talk. So let's talk about mathematics. So a basic question which I really like to introduce to you is why we partially sum in multiplicative number theory, right? So let me define actually what is a multiplicative function. Is any function that has this rule here, that rule that holds for all in integers coprime n and m. And a completely multiplicative function is any function that that property holds for all n and m, right? And what is special about these functions is that they are determined by the values that they take at prime powers, right? So actually completely multiplicative, you are determined by the values at primes, because the power k goes outside the value that you take at the prime. And well, we all know that from the computational point of view, to factorize integer n is hard from a computational point of view. And so to compute f of n is hard because you have to factorize n to compute f of n. So let me take here some. And so when we do partial summation for a multiplicative function, most part of the time, a structure might emerge in these partial sums, and the individual discrepancies of a single value of n, or f of n, they dissolve if the length of the summation is large, right? And so the partial sums, they return most part of the time the average value of your multiplicative function. So the first example of this phenomenon is I would like to talk about the divisor function, which counts the number of positive divisors of n. And the behavior of this function can be chaotic in the following sense. If you have a prime number, you have only two divisors, 1 and the prime. But if you shift your prime to plus 1, then you can be large as that quantity there that is quite large compared with 2, let's say. And this is another manifestation that addition and multiplication, they entangle in a strange way, right? You shift one prime, and you get a strange structure about your function. So here I made a graphic of the function of tau, right? So you see that you always, when you get a prime number, you go down below to 2, and you can be large several parts of the times. But you can see that there is a strong color in something right there happening, right? And actually, this strong color is around log of x. That is the average of the function tau. And when I do partial summation, these individual discrepancies dissolve. The curve that I get is this almost flat curve that is around here. So let me come back. You have the discrepancies of tau, and when you do partial summation, you get this flat curve. Actually, it's not a flat curve because a node theorem of Dirichlet says that the partial summations, there is a logarithm multiplied by x plus some error terms, right? So what Dirichlet proved, he proved that the error term that we call delta function is upper bounded by square root of x, right? And here is an isolated graph of the error function, and you see that it oscillates in both positive and negative values, in between large and negative values. And it's an open problem today to determine the largest fluctuation of the delta function, right? So the divisor problem that we call is the problem to obtain the infimum exponent alpha over all the exponents a, such that delta of x is less than x to the a. And so it's widely believed that alpha is equal to 1/4, right? And Landau unpublished and Harder published in 16 that at least alpha is at least 1/4, right? And the best upper bound up to date is due to Huxley. That is this exponent 131 over 416. That is approximately 0.31 and etc. And okay, so now I want to turn to a different question that attracted many attention from the number theorists in 15 or 10 years ago. That is the Erdős discrepancy problem that I'm going to state in the next slide. So the basic question for multiplicative functions I would like to make is, can a multiplicative function have bounded partial sums? So by bounded partial sums, I mean the existence of a universal constant C such that the partial sums up to x for all x are bounded by C. So this is bounded partial sums. And so you see now that different from the first slide, a single value f of n is important because suppose that I have my partial sums bounded by C. And if I change one value f of n, I can break the constant by C plus 1 or etc. Right? So now a single value is important. They do not dissolve if the length of the discrepancies of a single value do not dissolve if the length of the summation is large. So, okay, basic answers to this question, there is a trivial answer that I take f of 1 equals to 1 and f of n equals to 0 for all n bigger or equal than 2. This is a multiplicative function, of course, but it's a trivial example, right? So the non-trivial examples that we want to build is the examples where with positive density on the primes, your function does not vanish, right? So a non-trivial example is the alternating sequence. Well, why is non-trivial? Because at least for me, I was very surprised that this is indeed a multiplicative function, right? And this is the surprising thing. And well, I'm going to state in the next slide the Erdős discrepancy problem. And when I do a research in the literature about these examples, these extreme examples, I don't think that Erdős know this example for multiplicative function with bounded partial sums. Right, Alexi? It was only Kunz in 2010 that he wrote a paper on this, and he presented this example of multiplicative function with bounded partial sums. And so the Erdős discrepancy problem was the polymath project number 5, led by Kalau, Gowers, Tal. And in this polymath project, where many people collaborated in the web to build this theory, they established that the question of bounded partial sums for completely multiplicative, not for multiplicative only, for completely multiplicative, is equivalent to the Erdős discrepancy problem that I'm going to state now. So this problem asks if there exists a sequence of plus or minus 1 such that for some constant c, for all x and d, the function looked at through the homogeneous arithmetic progressions is always bounded by c. And so I have tried to do a research in the literature what Erdős had in mind when he established this conjecture. Well, I'm not sure if I'm going to talk is true, but we have the famous van der Waerder's theorem in coloring, right? So you color the positive integers with two colors, let's say pink and white. The van der Waerder's theorem for coloring says that you can always find a large arithmetic progression that you always find the same color. And so if you interpret colors are plus or minus 1, so you have always arithmetic progression where your partial sums do not cancel at all. You always sum always plus, plus, plus 1, or minus, 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 minus 1. So let's say your partial summation is large along this arithmetic progression. And so what Erdős is asking is what happens if I fix the first point of the arithmetic progressions, all of them starting at 1, right? So homogeneous arithmetic progressions. And so the Erdős discrepancy problem has been solved by Tal in 2015. And he used actually this fact of this reduction to completely multiplicative functions, right? So to establish the problem for general arithmetic functions of plus or minus 1 is equivalent to show that for a completely multiplicative function with values in the unit circle, the partial sums are always unbounded of this completely multiplicative function. And okay, so after the solution of the Erdős discrepancy problem, interesting research followed up. So I would like to mention here a paper from 2017 from Klurman that is right there, where he classified the plus or minus 1 multiplicative functions with bounded partial sums. So what Klurman solved in this paper is actually what has been known by the community as the Erdős-Kunz-Tal conjecture. And 1 year later, if I'm not mistaken, Klurman and Mangerel, they solved the Chudakov conjecture, which for me is a very surprising result, because let me say, if I remember Chudakov's conjecture, so suppose you have a multiplicative function in the unit circle, and the set of values, this hypothesis here, the set of values of your image is finite. The set of primes for which your function vanishes is finite. And F has bounded partial sums. Completely multiplicative. And F has bounded partial sums. Then, Alexei, are these the hypotheses of Chudakov's? Okay, so a function satisfying these 4 conditions must be a Dirichlet character, which is a special object in analytic number theory. So for me, this result is surprising because I like to think on the contrapositive of this result. Assume that a completely multiplicative function breaks one of these 3 hypotheses here, then your multiplicative function must have at least break one or forget about what I was saying. Okay, so this is what Chudakov's conjecture, and okay. Since my PhD, I was interested in multiplicative functions with support on the square-free integers, right? So my PhD thesis was actually about random multiplicative functions, but I remember that at that time, by around 2015, I was interested in to build a single example of a multiplicative function with support on the square-free integers that takes plus or minus 1 in the primes, that has more than square root cancellation. And so I end up, actually, this solution of the Erdős discrepancy problem, I would like to know something more, actually, if the multiplicative function can have bounded or unbounded partial sums in the square-free integers, right? So, okay, so I was able to prove actually that we can build examples of multiplicative functions with more than square root cancellation, actually. Cancellation x to the 2 over 5. So 2 over 5 is 0.4. Assuming the Riemann hypothesis, we can build these examples. And later, this paper was improved by Qiang Liu, a Chinese mathematician. She proved that actually we can build examples of 1/3 cancellation. And my guess is that we can go up to 1/4 cancellation. And tomorrow, my student, Kyle, that is right there, he's going to tell the generalization of these results to the K-free integers. And so, okay, in this paper that I mentioned in here, I was able to prove actually that a multiplicative function with support on the square-free integers has unbounded partial sums. And the method was exactly using the method of the first paper in this list, the Klurman classifications of plus or minus 1 multiplicative functions, where there are a lot of correlations formulas. And at the same time, this Erdős discrepancy problem over square-free integers has been solved by Klurman, Mangerel, Poirat, and Terevainen using a new method that they call rotation trick that actually, if I'm not mistaken, was used in another settings. For example, the Erdős discrepancy problem in function fields, right? And in this paper, actually, from 2022, they introduced the notion of modified Dirichlet characters. That is, when you take a Dirichlet character and you modify them in some finite set of primes. And they were able to prove that if you take a Dirichlet character and modify in at least one prime, the partial sums are omega of log of x. And they made a conjecture that if you modify in 10 primes, then it will be omega of log of x to the power 10. So in that paper that I mentioned here, I was able to prove that for some subset of modifications, the conjecture is true, actually. And so the last paper I would like to mention is the Erdős discrepancy problem over functional fields that I could not trace the exact year that it was uploaded to arXiv, but I just go to some page of the subset of authors, and I discovered that it's going to be appearing in MathAnally. So this is just a list of what happened after the Erdős discrepancy problem. So I would, my point here is that many things to investigate in this list. And 3 years ago, I started to investigate the consequences of the first paper of the list. So I'm going to explain more about the first paper of the list. So what Klurman proved in the paper of 2017 is that a multiplicative function taking plus or minus 1 values has bounded partial sums if and only if it is periodic and sum 0 inside the first period. Okay, but how we build periodic multiplicative functions with bounded partial sums? So a proposition inside this paper says that a plus or 1 multiplicative function has period m and sum 0 inside the first period, if and only if you have a rigidity in powers of 2. So your function always takes minus 1 at the powers of 2. And the other conditions, so for a power prime of a dividing the period, your function is stabilized in powers with the last value. And for each p coprime to the period, f of the powers equals to 1. And so what I was interested in was to drop the condition plus or minus 1 to general complex values, right? So what I was able to show is that the two last conditions of Klurman's theorem still holds, but the last condition here, let me come back here. This rigidity of powers of 2, that you always must be equals to minus 1, if you want to go to general complex values, you can substitute this by this rigidity condition here, in which your summatory function of the primes of prime powers of some prime dividing the period, that you have some 0 inside the period. And what you have to observe here, that is your function is only plus or minus 1. The only way to achieve this condition here is you always equals to minus 1 at the powers of 2. So, another important assumption to deduce this theorem is that f of the period must be different from 0. Because if f of the period equals to 0, then the argument does not work, because if you are feeling what the thing I can get, I would be in two classes. Because remember that Dirichlet characters, they vanish at the period, right? So I cannot, without this hypothesis here, I cannot deduce these three conditions. But the fact is, if I assume the three conditions, then f is m-periodic, has bounded partial sums, and f of the period may be 0 or not. So let's, so I want to call this class of functions by the C1 pretensions and Z periodic, this class of functions. And let me show some examples. So let's define for every prime different from 2, well, let's define f of pk equals to 1. And define f of 2 equals to minus 2. And at powers bigger than 2, define f of 2k equals to 0. Then the sequence you get is this periodic sequence 1 minus 2, 1, 0, that clearly has bounded partial sums in the first period, that is 4. So it has period 4. F of the period vanishes, and has bounded partial sums. So another example, now let's take our favorite prime equals to 3 and define outside 3 in powers equals to 1, and f of 3k equals to minus 2 for all k, right? So you get a three periodic sequence, 1, 1, minus 2, 1, 1, minus 2, and some 0 inside the period. So here in the first example, f vanishes at this period, and in the second example, f does not vanish in its period. And so an open question that I don't know how to answer is not the main question of this talk. So I know at least 2 classes of periodic multiplicative functions with bounded partial sums, the class I presented there, and the non-principal Dirichlet characters. So my question is whether there are other classes of multiplicative functions with these properties. I don't know how to answer. Okay, so now justifying the title of the talk, let me introduce the convolution, the convolution operation between arithmetic functions. So is this operation f star of g at the point n is that sum, defined to be that sum. And one of the basic questions that we learn in the analytic number theory book is that when you take the convolution of 2 arithmetic functions, the Dirichlet series of the convolution is the product of the two Dirichlet series in the region of both of them converges absolutely. And so the basic question that I want to treat in this talk, suppose that I have 2 Dirichlet series that have abscissa of convergence 0 and of absolute convergence 1. What can we say about the abscissa of convergence of the convolution? And so for you get a feeling of the zoology, the zoo you can get, let's take, for instance, the Möbius convolution 1. So both, oh no, this is don't have bounded partial sums. But okay, so you take the convolution, this convolution converges everywhere. It's not an example of my theory, but in general, if you take the convolution, this converges everywhere because one is the Dirichlet inverse of the other, and converges everywhere. And the Dirichlet series of one convolution Dirichlet character also has abscissa of convergence 1, right? Because you can use, for instance, you can show that the partial sums cannot be less than x, let's say. And so what can we say about the abscissa of convergence of the Dirichlet series of F1 convolution F2, where F1 and F2 belong to the class I introduced in the previous slides. And what can we say about the abscissa of convergence of the Dirichlet series of 2 non-principal Dirichlet characters? And let's mixture these classes, convergence of Dirichlet series of a character and a function in that class. So this is the basic questions I would like to tell you about. And okay, so in my paper of 2022, I proved that if F1 and F2 belong to the class C1 pretensions and 0 periodic, the abscissa of convergence is at most the Huxley exponent for the Dirichlet divisor problem. And inside a subclass, I proved that the abscissa of convergence is at least 1/4. So my conjecture at that time was that the abscissa is always at least 1/4. And so the main result is actually what I established in my collaboration with Olivier and Gopal Maiti and Priyanvad Srivastav, is actually that we proved this conjecture, and we proved that for any functions belonging to this class, the abscissa of convergence is always at least 1/4. And last year I was preparing an analytic number theory course to my students, and I used the book of Tenenbaum, and I discovered that actually there is a conjecture about the function that is covered by our example. He conjectured in his book, at page 216, that for the function that is the alternating sequence, the abscissa of convergence is exactly 1/4. He conjectures that. And our theorem actually says a partial answer to this problem that is at least 1/4. And as I'm going to show you in the next slides, this conjecture of Tenenbaum is so hard as the Dirichlet divisor problem. And so a work in progress is that similar results also holds for the convolution of two Dirichlet characters. And so I now give some comments on the proof of our main theorem. And so let's say that M1 and M2 are the periods of F1 and F2 respectively. So in my previous paper, I discovered this formula that I can express the partial sums of the convolution of functions belonging to that class with some linear combinations of the delta function from the divisor problem. And so, in particular, upper bounds for the Dirichlet divisor problem, they transfer immediately by the triangle inequality to the partial sums of the convolution. But the same is not true for omega bounds, right? Because, well, we know that each one of these deltas here are becoming large, so large as x to the 1/4. This is hardest result. But since I look to a linear combination in several scales, I cannot prevent by a direct argument, at least I could not find, a direct argument that prevent a conspiracy between these large values in such a way that they cancel each other. And I could obtain I could kill x to the 1/4 with another x to the 1/4 in a linear combination of them. But I must admit that this would be a large conspiracy among the delta function. If you remember the graph that I put in the first slide, that seems to be something like random. But the way we found to approach this problem is with a nice theorem from Tong from the 56, if I'm not mistaken, that is in the square mean sense, the Dirichlet divisor problem is solved. Because when you integrate the square value of the delta function, you obtain some constant that can be computed explicitly times x to the 3/2. So suppose that, forget about delta of x squared and put x to the 1/4 here inside the integral. If you square, x to the 1/4 goes to the x to the 1/2, and when you integrate, you go to x to the 3/2. So in some sense, in the square mean sense, the Dirichlet divisor problem says that actually, yes, your divisor problem oscillates in a scale of x to the 1/4. And so our theorem follows if you could prove that the mean square average of the partial sums are lower bounded by some positive constant times x to the 3/2. So this would imply that the function inside the integral cannot be little o of x to the 1/4. And so if we open the square and take the limit, what we found is a quadratic form where g of n is the big convolution, the 4 convolution, and the coefficient c and m is a matrix term that we call the correlation between the terms of the delta function, right? And so the question to prove our theorem reduces to whether to show the matrix C and M is positive definite. Because if it is positive definite, the eigenvalues will be always positive, and I will have this limit here, this quantity here, I will have this consequence of the matrix being positive definite. And so the next work we proceeded was to investigate the matrix structure of these coefficients. So any question up to now?
delta squared. What about moments like x to some power times delta of x squared?
Well, I'm not sure, but I think that something exists and is in the book of Ivich, at least. Yeah. Do you know anything about these moments of the delta function, Livich?
No, but it's by analogy with the Riemann-Zeta function moments or something.
Ah.
Should be interesting.
I see. And so the next step we done in our work was to compute explicitly the correlation. And what we proved, we compute explicitly in terms of n and m, this integral here that is given by this expression has an Euler product actually, and actually an important step to prove this result was the truncated Voronoi formula that we have for the delta function, that is that the sum of that cosines, and actually to prove that theorem, at least analytically, the analytical part is not difficult because you have to only to manipulate integral of product of cosines, and you have to control some error term that is of this order of magnitude. And so we reach that actually this correlation here is actually given by this series here of tau of Cn times tau of Dn. And I know that this sum of tau of Cn, tau of Dn, this linear correlation, appeared in several papers when we proved it, at least in a recent paper by Shiparsky, how do you pronounce? Shiparsky and Munch. They arrived in similar computations here, but they were not able to finish the computation of this series independence of C and D. And I remember very well at this step that Olivier told me in Marseille to prove this result here. Is prove that if f is multiplicative, f of c is different from 0, then f of c times n divided by f of c is also multiplicative. Actually, I didn't believe in this result, and I was a bit lazy. I didn't believe it at all. And Olivier tried to say that this was proven somewhere by Motohashi, if I'm not mistaken. No? And okay, I was a bit lazy, but we have brilliant postdoc students that they give a very short proof of this fact here. And you can see the paper. And well, it, at least for me, is strange because the primes of C may entangle with the primes of N, and this at the end may not be multiplicative. But with this result here, I only divided this sum by tau of C, by tau of D, and evaluate just an Euler product, this sum here, and I obtain the explicit dependency between C and D of the linear correlation. And a byproduct study that we study in our paper, what can we say when I integrate the correlation with irrational number? So in the previous slides, I have theta was rational, but what can we say when theta is a rational number? So what we proved is that there is a decorrelation when theta is irrational, and we can say a little bit more. If theta has finite irrational exponent, then we have a power saving in the cancellation. And more generally, okay, so by the continuous theorem that says that almost all irrational number has finite rational exponent equals to 2. So we can say something that holds almost surely with respect to the Lebesgue measure. We have that cancellation over there. And so another study that is going to be uploaded to arXiv soon is by my student. He investigated what can we say when you have irrationally measured psi, let's say. We define it this way, right? So you can approximate at most with psi velocity. So for some continuous function, non-decreasing, and function we can approximate in this way. So what he proved, actually he proved something more strong that he told me in the last, where he's right here, there. He proved that he could obtain exponent x to the exponent 3/2 here on this thing. So the thing is the following. If you can approximate exponentially fast your convergence in the Diophantine approximation, then you get cancellation x to the 3/2 divided by log of x. So if you can approximate two double exponential, then you get cancellation log of x. So for any function psi, you can build the psi minus 1 and show that you have this cancellation, and etc. So going back to the main line, we proved that actually the structure of the matrix of the correlations is some multiplicative function phi that should not be confused with the Euler's phi function. Is any multiplicative function phi, and from evaluated at the least common multiple of n and m divided by the greatest common divisor. So this is the matrix entanglement of our correlation matrix. And how? This kind of matrix, we didn't find anything about this kind of matrices in the literature. So we proceeded in general lines to prove some conditions when this matrix is positive definite. So with some additional hypotheses over phi. So for instance, if phi is completely multiplicative and satisfies other bounded assumptions, then with the Selberg diagonalization processes in Sievre theory, we can show that actually the matrix is positive definite. And the end of the proof of our theorem actually ends up by found a conjugation of our original matrices to reach to a matrix that's somehow approximated by a matrix related to a completely multiplicative function. So the conjugacy property does not interfere in the eigenvalues, and so this is how we prove the positive definities of the original matrices. And so I didn't have a lot much to say, and this is all I have to say. 40 minutes.